Before there were planets, oceans, or even Earth, there was only a vast cloud of gas and dust, collapsing beneath its own gravity.
Welcome aboard. I'm Captain Elena. Today we're witnessing the birth of a star. From a cold cloud of gas and dust to the moment gravity ignites a new sun. Let's begin.
The sun did not suddenly flash into existence. Long before ordinary hydrogen fusion became its main power source, the young sun was already fiercely luminous, heated by falling material and gravity's relentless squeeze. Gas from the inner disk followed powerful magnetic fields onto the star, striking irregular high-latitude regions in brilliant accretion shocks. Every impact added mass, heat, and energy. Inside, the young sun was almost entirely convective. Immense currents of plasma rose from the depths, spread beneath the surface, cooled slightly, and sank again, an entire star overturning as one continuous, pressurized fluid. Gravity kept pulling inward, but the star was not in free fall. Its hot interior produced enough pressure to support its spherical shape. This hydrostatic balance allowed the sun to contract slowly instead of collapsing in an instant. Over millions of years, the young sun became smaller and less bloated. Its center grew hotter, yet its total brightness generally fell because its glowing surface area was shrinking. Accretion weakened, magnetic activity eased, and the surrounding disk gradually thinned. This was not a visible switch. The star changed almost imperceptibly from the outside, while deep within, temperature, density, and pressure continued climbing toward the conditions required for lasting nuclear fusion. Its internal architecture also changed. Large-scale convection retreated toward the outer layers, while a dense, opaque radiative region developed around the center. There, energy moved mainly through countless interactions with matter and radiation. At these depths, ordinary atoms could not survive. Electrons moved freely through a dense plasma, while hydrogen nuclei raced through the core at enormous speeds. At roughly 1 million Kelvin, trace deuterium began to fuse. This temporary fuel slowed contraction, but the supply was tiny and soon ran low. Ordinary hydrogen was much harder. Protons repel one another, and almost every encounter fails. Quantum tunneling gives a rare few the chance to reach nuclear force range. In an extraordinarily rare weak interaction, one proton changed into a neutron. The pair bound together as deuterium, releasing a positron and an electron neutrino. The positron soon met an electron, releasing gamma radiation. Deuterium then captured another proton to form helium-3. Finally, two helium-3 nuclei combined into helium-4, returning 2 protons to the plasma. The final products contained slightly less rest mass. That difference emerged as energy. Neutrinos escaped within seconds, but radiation faced a far slower journey. Energy from the core was absorbed, scattered, and re-emitted again and again. Its outward random walk could take hundreds of thousands of years. Near the surface, convection carried that energy through the final layers and released it into space. Fusion began as a microscopic trickle, then gradually supplied more of the sun's power. Gravitational contraction became less important until nuclear reactions replaced the energy continually radiated away. The sun had settled onto the main sequence. Around it, the remaining disk was still transforming. Microscopic grains collided and clung together through electrical forces. Clusters became pebbles. Pebbles concentrated into larger swarms, and gravity gathered the most successful regions into kilometer-scale planetesimals, the first true building blocks of planets. Those planetesimals collided, shattered, merged, and collided again. The largest bodies swept up their neighbors and became rocky protoplanets. Each impact changed their spin, composition, and orbit, while the inner solar system slowly cleared of loose material. Impacts, compression, and radioactive decay heated these young worlds. Many became partly or completely molten. Dense iron and nickel sank toward their centers, while lighter silicate rock formed mantles and early crusts, a process called differentiation that built the layered interiors of the terrestrial planets. As bombardment slowed, surfaces began to cool. Volcanoes released gases from the interior, and water came from several reservoirs, material already trapped inside the growing planets, and water-rich bodies arriving from colder regions farther out. Beyond the warm inner system lay the frost line. Here, water, ammonia, methane, and other volatile compounds could freeze into solid ice, creating much more material from which distant worlds could grow. Rock, metal, and ice assembled into larger outer system cores. Some became massive enough to capture hydrogen and helium before the young sun's radiation and winds dispersed the remaining gas disk. Their atmospheres expanded rapidly, surrounding dense interiors with thousands of kilometers of compressed gas. Jupiter and Saturn became the dominant worlds of the outer solar system, enormous planets that absorbed, scattered, or redirected nearby material. Each was surrounded by a rotating circumplanetary disk, where smaller particles gathered into moons, rings, and countless lesser bodies. The giants did not grow in isolation. Their gravity carved gaps in the solar disk, stirred nearby debris, redirected comets and planetesimals, and altered the paths of neighboring worlds. The young solar system was a changing network of resonances, encounters, and competing gravitational pulls. Farther from the Sun, Uranus and Neptune grew from mixtures rich in rock and ice. They captured hydrogen and helium too, but not enough to resemble Jupiter and Saturn. Their interiors remained dominated by heavier volatile materials under enormous pressure, making them a distinct class of worlds, the ice giants. As the giant planets exchanged energy and angular momentum with the surrounding debris, their orbits shifted. This migration rearranged the outer solar system and scattered countless small bodies both inward toward the planets and outward into distant darkness. Not everything became a planet. Between Mars and Jupiter, a surviving population of rocky and metallic bodies remained in the asteroid belt fragments, shattered protoplanets, and unfinished building blocks from the solar system's earliest age. They preserve a record of conditions that existed before the planets were complete. Jupiter's powerful gravitational influence repeatedly disturbed their orbits and helped prevent the region from assembling into one large world. Later, collisions shattered, melted, and rearranged the survivors. Some meteorites reaching Earth today are pieces of those ancient bodies. Beyond Neptune, the cold outer disk left another population of remnants, the Kuiper Belt, a broad region of icy worlds and smaller debris. These bodies preserve frozen water, methane, and other ancient materials from the environment in which the outer planets formed. Pluto is one of its best-known members, but it is only one among many frozen worlds. Some have moons, some follow tilted or elongated orbits, and many have changed little since the solar system was young. Farther still, scattered objects may form the Oort Cloud, an immense spherical reservoir of ancient ice surrounding the solar system. From a collapsing cloud to a dynamic system of worlds, this is how our cosmic home began.